Okay, now for the next part. Some teachers will call this a rice box, but I'm going to show you how to calculate the Ka for an acid if you're given the pH, which is the next batch of problems in the book. So the RICE acronym stands for reaction, initial, change, and equilibrium. So it's a rice box because you always want to show the information in this table before you try to do your math. Okay, so the reaction we're going to do is for the weak acid, hydrofluoric acid, which is going to split to form some H's and some fluorides. Okay, if we make a 0.1 molarity solution of hydrofluoric acid, then we have an initial concentration of 0.1, and we didn't have any H or any F at all before we started. But once we mix it, some of this 0.1 is actually going to split. So we're going to lose some of it. And for every one that splits, we're going to get one of those and one of those. And so you can think of it as, here's where we start, here's what's happening. So at equilibrium, we should have 0.1 minus X of the aqueous hydrofluoric still. And then we'll just have X and X of that. Okay? Now, we're calculating the Ka using the pH. The beautiful thing is, if we know the pH, we can turn it into the concentration of H using our equations from before, which allows us to just substitute that answer everywhere where we see an X to figure out the Ka. So that's what we're going to do. Okay? And for this solution, the pH would be 2.1 for hydrofluoric acid. So what we're going to do is we're going to calculate the Ka for hydrofluoric acid, which should be at equilibrium X times X, right? It's the products divided by the reactants, but this is 0.100 minus X, okay? But luckily for us, because we know this information, we'll be able to figure out how much H plus there is, and we can avoid using the quadratic formula down here. We will do one where you need to do the quadratic formula, so we'll get to that. But just from last part of the video, if we know the pH is 2.1, then we know that the hydrogen concentration must be the anti-log of that. So on your calculator, you type second log, which will give you 10 to the power, and then you type negative 2.1, and your calculator should give you 7.9 times 10 to the minus 3. And so what that means is, when we mix this solution and we let it sit there and reach equilibrium, it will have a concentration of hydrogen ions of 7.9 times 10 to the minus 3. And because we set up our rice box, we know that X is the H plus. And so now we can substitute this number for every X down here. So we get 7.9 times 10 to the minus 3 squared divided by 0.100 minus 7.9 times 10 to the minus 3. If you have your TI 83 or 84, this should be stored as your last answer, so you can easily just do the second, and then above the minus sign down at the bottom has the word answer, ANS. So if you just do ANS, push the square button, and then divide by parentheses 0.1 minus the ANS your calculator should give you the correct 6.9 times 10 to the negative 4 for the Ka. Okay? So if you have a solution and you want to know what the acid is, you can put a pH meter in there, get the pH, okay, run through the Ka, and you get this number, which is the Ka for hydrofluoric acid. You can help identify an acid by using the Ka. Okay? But this is how you do it. Okay? And we're going to be using these rice boxes a lot for the rest of the year. So make sure you understand what we're doing here. Reaction, initial concentrations, change in concentrations, and then equilibrium concentrations. All right, so now we're going to walk through and we're going to solve for the concentration of H plus, if we already know the Ka, figuring out what would be the pH of the solution if we're going to use hydrofluoric acid. So we're going to use the answer from before, right, which was 6.9 times 10 to the minus 4 is the Ka of this acid. Again, to solve this, we need a rice box. So here is what our equation is. Again, let's pretend that we're going to just make a 0.1 concentration hydrofluoric acid, which means we start with 0 of that and 0 of that. Just like before, we're going to lose some of this. We're going to gain equal amounts of that, which means at equilibrium, it's 0.1 minus x, x, and x. Okay? So you'll notice this rice box looks exactly the same as when we went the other direction. The other way was a little bit easier math-wise, which is why we did it first. Okay, so last time we knew the pH, and we wanted to find Ka, which meant it was easy for us to find x, so that we could figure out the Ka. But we might be trying to make this acid in the lab, and we already know it's Ka from the textbook. So now we want to figure out what pH will this be at if we make it. Because if it's too acidic, it could cause some problems for you. Or if it's not acidic enough, there's a reason why we need to know the pH. So what we do is we set up our equation for Ka the same way we would have before. So it's the H plus, which is x times x, divided by the 0.100 minus x. And the only thing that is not that fun this time around is that we don't have a way of solving for x. We just know that when we do this, our Ka is 6.9 times 10 to the minus 4. And this is where your math skills come in. If we're going to solve this for x, we've got to start simplifying it. So this becomes x squared divided by 0.100 minus x. So in order to simplify this, we got to multiply both sides by this denominator. So we're going to remove it from there and bring it over here. So we have 6.9 times 10 to the minus 4 times 0.100 minus x equals x squared. We'll distribute this through, so we get 6.9 times 10 to the minus 5 minus 6.9 times 10 to the minus 4x equals x squared. And now we're going to bring both of these over to the other side. So we get x squared plus 6.9 times 10 to the minus 4x minus 6.9 times 10 to the minus 5 equals 0. And at this point, you now have to recognize that this is ax squared plus bx plus c equals 0, which means that the solution for x is the quadratic formula. So it's the negative b plus or minus the square root of b squared minus 4ac all over 2a. If you have one of the TI calculators and you want to program your calculator to do the quadratic formula for you, I'll make a video and post it on how to do that in a little bit. Okay, but for now, I'm going to run it on my calculator just so we get an answer and I show you what we would get. Otherwise, you're going to have to do this by hand. Okay, and it takes a while, but this is how you solve it for math class. If you run this equation through the quadratic formula, okay, which I have it on my computer already, so I'll go to quadratic formula. A is 1, B is 6.9 times 10 to the negative 4, and C is negative 6.9 times 10 to the negative 5. And my calculator spits out 8.0 times 10 to the negative 3. Okay? Now, that answer is very, 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 very close to what we had on the last problem, 7.9 times 10 to the minus 3, which is why we know it's correct, okay? Because it's within a sig fig of where we were at. But that means that that is the concentration of H+. So if we know that the pH is the negative log of that, you do the negative log of that number. And where is it? So the negative log, and I get 2.1, which was the number we started with before. Okay? So now I've taken you from, if you know the pH, how do you get the Ka? And if we know the Ka, how do we get to the pH? Going from the Ka to the pH requires the quadratic formula. So if you've got a calculator that you can program the quadratic formula in there for you, it'll save you a lot of time. Okay? And that's the end of section 3. So next we're going to move to section 4. Neutralization reactions. Okay, so because acids and bases are opposites, when we mix them, their solution always becomes closer and closer to neutral. So if we add equal amounts, we should eventually become equal. But here's the basic equation for all neutralizations. If you mix an acid and a base, you'll always get a salt and water. So an example of that would be hydrochloric acid plus sodium hydroxide would make sodium chloride, table salt. And as we said all year long, if you ever have an acid and a base, write the water as HOH, because then it's easier to see the double replacement that's taking place. Okay, so all acid-base double replacements should form a salt and a water. Okay, so the way it's used is what's called a titration. So in a titration, you stumble across a solution that is acidic. So the one we're going to use is acidic. So its pH is going to be down here somewhere. Okay, you're going to put it in a beaker, or you're going to put it in a container. And what you're going to do is you're going to add a known amount of a strong base. So if you have an acid, you always want to add a strong base. If you have a base, you always want to add a strong acid. Okay? By adding strong acids and strong bases, you're forcing the base will chew through the acid whether the acid is strong or weak. Okay? And what will happen is you will add sodium hydroxide, and this graph will slowly go up, and then you will get something that looks like this. Okay? It becomes very, very steep very, very quickly. So you have to be very, very careful when you're doing this. And the virtual lab we have to do this on, if you go too far, 1 milliliter can take you from way down here all the way to way up there. So you've got to do it very, very, very carefully. Okay? But what we want to do is we want to reach the center of this giant curve. So I'm going to put a dot right there. Okay? And this is an important place on the curve. It's called the equivalence point. Okay? So what the equivalence point is that is the point at which the amount of H plus you've added from the unknown is now equal to the amount of OH from the base that you've added. Okay? Which brings us to an old equation. Okay? Because when we measure this base, we know that the base has a molarity, and we're using a specific volume of it. Okay? And we're trying to reach a point in which the molarity of the acid that we started with, which we don't know, also had a volume. So if you remember back when we were doing dilutions, it was M1V1 equals M2V2. So we're using the same equation as a dilution to figure out the unknown acid using our equivalence point. Now here's where the math from section 1 comes back in. Okay? Sodium hydroxide is monohydroxic. So because it's easy to accidentally forget that a base or an acid is monoprotic or diprotic or triprotic or monohydroxic, etc., there are some books who teach a new unit called the normality of the acid and the normality of the base. Okay? So some books will teach this word normality, some books won't. Your book does not. It just expects you to remember if your acid was diprotic, you have to multiply by 2. If it's triprotic, you have to multiply the molarity by 3. Same thing on the base side. So some books will add a little I here to remind you that you have to multiply by however many hydrogens the acid splits into, and multiply the base by how many hydroxides it splits into. I don't care which one you use, you just have to show that if this was calcium hydroxide, for example, if we made a 0.5 molarity calcium hydroxide solution, you would have to do 0.5 times 2, or you can just do the M and the I together and say it's a 1 normality calcium hydroxide solution. Every book is different, so I'm teaching you both in case the next chemistry class you take uses normality, you've at least seen it before. But I don't care if you use that one or that one. Okay? But the solution is all the same. So let's say we had 25 milliliters of an unknown acid, okay? And we used a 0.25 molarity sodium hydroxide, like we originally had said. And let's say that by the time we got to the equivalence point, we had added exactly 10 milliliters of base. Okay, and we'll go 2 sig figs on all these numbers. We can now calculate the molarity of the unknown acid, assuming it's monoprotic, or what we're really calculating is the normality of the original acid. But all we would do is do 25 times 10, or sorry, 0.25 times 10 divided by 25. So the molarity of the unknown acid would be that divided by that, which would be a 1 over 100 times 10, 0.10 molarity of the acid. At that point, you would then have to know if this acid was monoprotic or diprotic or triprotic to do anything from there. Okay? But this is an old formula that we've used a long, long time ago. So if you need to go back and do some of those dilutions to remind yourself, that's fine. Okay? But it's really important that we understand this is the point we're trying to reach, the equivalence point. Okay? The book then gives you a bunch of indicators that will change colors depending on the pH. And it throws another vocabulary word at you, which is called the endpoint. The definition of the endpoint is the point at which the indicator changes color. So if you know your equivalence point is going to be at 7, okay, then you want to pick an indicator that will change color at 7. So you got to look on the little table in the book, and some of them will change color at 7, some of them will not. But you need to pick one where the end point will happen at the equivalence point. Because otherwise you're just adding stuff, and by the time it changes colors, you might be way over here because the indicator you chose doesn't change color until 10. You want to make sure that you choose an indicator where the end point will be at the equivalence point. All right, the last thing in chapter 19 is the idea of salt hydrolysis. So on the last problem we did, if you asked yourself, but Miller, if we're doing an acid-base titration, isn't the equivalence point always going to be at 7? That's not always the case. Generally, it's only 7 if you have a strong acid and a strong base, which we will get to. Unfortunately, because acid plus base can make salt and water, we can also get salt mixed with water can create an acid and a base. So this ties into reversible reactions. Not only can the reaction go forward, but the reaction can also go backwards. So salt hydrolysis is when we're keeping track of this second one. Okay? So what you've got to do when you're thinking about it, let's use sodium chloride for example. Okay? Sodium chloride, if you mix it with water, and I'm going to write water as HOH again, okay? If the salt is going to split the water, it will create sodium hydroxide as the base, and this hydrogen will go with the chlorine to produce hydrochloric acid. So it's the same example I gave you for neutralization, but we're trying to figure out if the salt and the water will create an acidic solution or a basic solution or not. Okay? And now this ties us back into the thing we learned on the very first video from this chapter. Hydrochloric acid is a strong acid. Sodium hydroxide is a strong base. So what that means is that sodium chloride is a salt composed from a strong acid and a strong base. Anytime you have a strong acid and a strong base, the solution will always be neutral. These two are going to make sure they neutralize each other, and it's going to keep the solution neutral. So if you take table salt and you put it in water, and you put a pH meter in there, it's going to tell you 7.00. Okay? Because table salt comes from a strong acid and a strong base. If we were to use another salt, like ammonium chloride, okay? I'm actually going to change the color of this. Okay. To make it easier. If ammonium chloride is going to hydrolyze the water, right, going to perform hydrolysis, it's going to create NH4OH, and it will form HCl. Okay? Now, this will decompose into ammonia and water, but we don't need to know that for now. All you have to do is ask yourself, is this one of the 6 bases that I asked you to memorize that are strong bases? The answer is no, which means if it's not a strong base, it must be a weak base. Is hydrochloric acid one of the strong acids? It is. Okay? So what this means is you now have a salt that is composed of a strong acid and a weak base. So if you have a strong acid and a weak base, the acid is going to completely neutralize the base, and you're going to be left with an acid left over. So this solution would be acidic. Okay. And then we're going to pick another salt. I might have enough room down here. So now let's do, I'm trying to think of one. Potassium. Let's do, not sulfate. Potassium. Phosphate. Okay. If the potassium phosphate performs hydrolysis, you're going to get KOH, and you're going to get H3PO4. Okay. Now, even though phosphoric acid is triprotic, it is still not one of the 6 that's a strong acid. So this is a weak acid, but potassium hydroxide is a strong base. So if you have a weak acid and a strong base, then the base will neutralize the acid and you'll still have some base left over. Okay? So these are the 3 possible answers to any salt hydrolysis question. You're either going to get a strong acid and a strong base, which is neutral, strong acid, weak base, which is acidic, or a weak acid and a strong base, which is basic. Okay? And every year, kids always want to ask the question, well, what happens if it's a weak acid and a weak base? For my class, if you ever get that, just say it's neutral. But I'm going to put a star next to it. But that would actually require you to do a lot of math and figure out, is it truly neutral or not. So that is one you're going to do in another class that's harder than the high school level. So in regular chem or honors, you should probably only ever see those three. If you ever get a weak acid and a weak base, then it becomes a bunch of math with the Ka and the Kb. But I will let your chemistry teacher at the next level handle that. Okay? The very last thing in the unit is the idea of a buffer. Okay? For high school chemistry in my class, all you need to know is that buffers resist changes in pH. So what happens is if you have a buffer, if you add a little bit of acid, it's set up to where that acid won't affect the pH of the solution until you reach a certain point. Same thing with the base. Okay? And notice how I said up until a certain point. There comes a point where the buffer cannot resist changing pH anymore. So the word for that is the buffer capacity. Okay? And that's the point in which the buffer can't resist the pH change. Okay? There's a lot of complicated math on how to do it. We don't need to do it in high school. You will learn how to do it when you take UChem next year or when you go to college. Okay? But for high school chemistry, you just need to know buffers resist changes in pH, and the buffer capacity is the point in which the buffer cannot resist pH change anymore. Okay? So you're able to add a certain amount of acid before the buffer runs out, or you're able to add a certain amount of base before the buffer runs out. The way it works is pretty much Le Chatelier's principle and the common ion effect. Okay? So what happens is, if you remember what those are, okay, Le Chatelier's principle says that if you have a system at equilibrium, if you disturb that equilibrium at all, the chemicals are going to push one way or the other to try to relieve the stress. And the common ion effect is pretty much the same thing. If you add a common ion with another chemical, if one of them goes up, the other one must go down to relieve the stress. So what a buffer is you've either got to have a weak acid mixed with a salt that contains the conjugate base, or you need to have a weak base and a salt that has the conjugate acid. Okay? So for example, okay, if we had ammonium hydroxide and we mixed it with ammonium chloride, that would make a buffer. Okay? You have a common ion, and so what will happen is one of the two, either the base or the salt, will react with the acid to just create more of the other one, which will resist the pH change, or the salt will react with it to create the other one. One of them will react with the acid to keep the pH steady. One of them will react with the base to keep the pH steady. But there comes a point in which they run out. Okay? Hopefully that makes sense. Another one would be acetic acid, which you guys call vinegar, and like sodium acetate. Okay? Again, this will react with the acid or the base to produce more salt, to keep the pH steady. This would react with the other one to keep these chemicals, using Le Chatelier's and common ion effect, will keep the pH relatively constant until you use up one of the two. You don't have to go into all the math of it. You don't have to, you just need to know that in order for it to be called a buffer, it's got to be a weak acid with a conjugate, or it's got to be a weak base with a conjugate.